Okay, now this part here we will be looking at dual combustion cycle. The dual combustion cycle. Excuse me. Now, dual combustion cycle, as we know that it consists of one constant pressure, two constant volume, and two isentropic process. So altogether, there are 5 reversible processes involved in dual combustion cycle. So in this part here, I am using the questions to explain, okay, questions here, an example here, a work example here to explain how the dual combustion cycle works. So as you can see from point 1 to 2, from the PV diagram, point 1 to point 2, this point 1 to point 2 here, okay, that is an isentropic process. That is a reversible isentropic process from point 1 to 2 on your PV diagram. And that is the isentropic compression. Then from point 2 to 3, that is where you have your constant volume process, and that is constant volume heat addition. So as you look at PV and TS diagram at the same time, you can see 2 to 3 on the TS diagram. It does show that there is an increase in entropy. There is an increase in entropy from your TS diagram. Okay, so that is by referring to the PV diagram at the same time, you can see that is a constant volume process. So therefore, we call it as the constant volume heat addition. Then from 3 to 4, from this point 3 to point 4 here on your TS diagram, that is a constant pressure process. Constant pressure. And then on the TS diagram, you can see that is an increase in entropy. So that is constant pressure heat addition. 4 to 5, point 4 to point 5 here, that is isentropic expansion. That is an isentropic expansion process. So on the TS diagram, you can see that is a straight vertical line, okay, from 4 to 5. So isentropic. And then 5 to 1 is where you have your constant volume heat rejected or heat rejection. So from 5 to 1, you can see from point 5 to this point 1 here, there is a decrease in entropy. So that is basically how your dual combustion cycle looks like on your PV and TS diagram. Okay? So based from the question, they say that an ideal dual combustion cycle has a volume ratio for the adiabatic compression of 15 to 1. So the adiabatic compression, that is from point 1 to point 2. It is not point 4 to point 5, okay? Point 4 to point 5 is referred as the isentropic expansion process. It's referred to as the isentropic expansion process. So that is a point 4 to point 5. Okay, point 1 to point 2 here, that is your isentropic compression. So they have given us the volume ratio of 15 to 1. So you will have Vmax that is V1 over Vmin that is V2 is equals to 15 to 1. Okay. So and then at the beginning of the adiabatic compression, here, at the beginning of adiabatic compression, okay, they have given us the pressure, the volume, and the temperature. So that is 97 kPa for pressure. 97 kPa is equivalent to 0.97 bar. And then they have given us the absolute volume, 0.084 meter cube. So that is in meter cube that is in meter cube. So from there we can find out the mass of air actually. And then they have given us the temperature, 28 degrees Celsius. So when you add it with 273, absolute temperature of 301 Kelvin. okay, respectively. So that is referring to only the point 1, 97, 0.084, and 28 degrees C. Those refers to point 1, state point 1. The maximum pressure and temperature, the maximum, so the question here say that the maximum here, maximum pressure, temperature of the cycle is being 6.2 megapascal. So 6.2 megapascal is actually equals to 62 bar. 62 bar. Okay, and then 1320 degrees C, add it with 273, so you have 1593 Kelvin. So what you need to do is substitute all the pressure, volume, and temperature, okay, into the table here. Okay, so here you have 5 rows, 1, 2, 3, 4, and 5. So, and then you have your pressure column, volume, and temperature. So your pressure, substitute 0.97 bar here, and then the volume, 0.084 meter cube, and the absolute temperature, 301 Kelvin. And then the question said the maximum pressure and temperature. Maximum pressure is 62 bar. So when you refer to your PV diagram here, this PV diagram here, okay, so the highest most pressure is your 0.3 and 0.4 here. So that means that your P3 and P4 is equal to 62 bar. And then the maximum temperature given is 1530 degrees C, that is equivalent to 1593 Kelvin. So you look for the highest temperature on your TS diagram. That should be your T4. Your T4. Okay. So fill up everything into the table. So since it's constant volume from 0.2 to 3 and 0.5 to 1. 0.5 to 1 is having the same volume. So you put in your 0.1 absolute volume and your 0.5 absolute volume. And then 0.3 to 4 is where you have your constant pressure. So you put in your pressure, which is the maximum pressure, 6.2 or 62 bar. So that is for 0.3 and 0.4. So, and then based on the isentropic compression, from 0.1 to 0.2, so here we have state 0.1 to 2, and we know that W1 is equal to 0.084 meter cube. So by applying the volume ratio that we have, that is given in the questions, remember, is V max to V min, then only you have 15 to 1. So if you take 1 to 15, then you have to take V2 to V1. That means V2 over V1 is 1 over 15. V1 over V2 is 15 over 1. So from this, you have your, okay, so that is your V1 0.084. Okay, and then divided by 15. So you can find out your V2. That is 0.0056 meter cube. Then you substitute your 0.0056 into the table. Okay, filling up the table. Okay, please. Then the next thing, okay, then of course your 0.3 as well, because we know that from the PV diagram 2 to 3 is actually a constant volume. So your V2 and V3 is the same. Then you use your isentropic, okay, formula, relationship between the pressure and volume to the power of gamma here, in order to find out your P2, because since you have got your volume ratio of V1 to V2 is 15, and gamma for A is 1.4. So you can use 1.4 for the adiabatic index, that is the gamma. So from here you can find out your P2 by, okay, putting your P1 as how much? 0.97 bar. That means times 10 to the power of 5. Or you don't have to, because you are finding out P2 here also, which is also in bar. So your P2 will be in bar. So you have this, and then you have this. That is your P2 42.98 bar. So put this, okay, P2 into the table. So filling up this space here. So you have 42.98 bar. Okay, so then when you look into the table, so this is a space here, which an empty space here, okay, that is at point 2 and temperature T2. So we can find out T2 here, okay, by either using the isentropic relationship, or you can use the PV equals to RT. But before you use the PV equals to MRT, okay, first, based on these three values here, you have to find out your mass first. Find out your mass by using PV equals to MRT for this. Okay? Either way, you can use either way. So I have used the isentropic relationship between temperature and volume. Remember, temperature to volume is power of gamma minus 1. Pressure to volume is power of gamma. If you take temperature to pressure, then this should be gamma minus 1 over gamma. Okay, so you have this. Then you have T2 is equals to 889.2 Kelvin. So put it into the table here. Okay, so that is 889.2. So you have 889.2 Kelvin here. Follow? Then the next, excuse. So from this, that is your ideal gas law. This is your ideal gas law. So the purpose here, because we know that we have got P1, we have got V1, that is absolute volume, and then the T1. So from this, we can find out the mass actually from this. Okay, so substitute your P1, which is 0.97 bar, your V1, which is 0.084 meter cube, and then your temperature 301, and your specific gas constant should be 0.2871 times 10 to the power of 5. So you can find out your mass, that is 0.0943 kg. Okay? Next slide. So from the table, okay, so these are the data that we have got. And then what we need is now this point 3 here. The point 3. So the point 3, you can use P3V3 equals to MRT3 to find out the T3. Or from, excuse, point 4, okay, by using the ideal gas law, P4V4 equals to MRT4, where you have found out the mass just now. So mass for a reversible process, or a controlled mass system, or a closed system, we are actually referring to a closed system. So the mass is always a constant. Because a closed system is known as a controlled mass system as well. That should be taught in your Thermo 1. So this mass, we don't need to put M1 or M2 or M3 or M4, because this is a constant for a closed system. Okay? So we have this. The purpose is to find out this V4 here. The V4 here. So by substituting in all the values that you have from the table, you will be able to find out your V4. So that is 0.00695 meter cube. Okay, so you can put in your V4 here. That is 0.0695. Okay. Sorry. Now the rest of this space here, okay, I need you to do it now. Okay, to do it now so that you can fill it up. Okay, and then find out the rest of the parts that the questions are requesting or asking. Okay, so this is for the dual combustion cycle in general. Okay, so we'll continue later on in the next slide. Okay.